Então, só para revisar rapidinho. So just to recall, so we are interested in tunneling in a double well potential, so that was the potential, generic potential which has two minima, and we were interested in calculating the transition amplitude or the transition probability to tunnel from one minimum to the other. And the main idea was to use, path integral methods and to use a semi-classical analysis of this problem. And the first thing we encountered is, well, if we just do the usual thing, express this in terms as a sum of all classical paths connecting those 2 points, we immediately find that in the regime that we're interested in, which is that the kinetic energy of the particle is much smaller than the potential barrier, well, we don't have any classical path connecting these 2 points. So the idea was then, let's do what we said, let's take serious that we can study a related problem where we allow the time to be a complex variable. So in this case, we just change to purely imaginary time and study this related problem. And then once we can solve this, we can see if we can analytically continue by substituting tau to IT to find the answer to the problem we were interested in. Now the advantage of doing studying the problem in imaginary time was that in the imaginary time formalism, the action that describes, that gives the weight to the path, has inverted sign between the kinetic and the potential energy. This means in the imaginary time formalism, we are studying this problem where now we have 2 maxima, and there we have classical solutions connecting these 2 points in the time t. Okay, so that was the main observation. And then what we did is just starting then, so what we want to do is an analysis of this object in the semi-classical approximation, so a sum over all classical path, and then we have some fluctuation determinant contribution, and then the imaginary time action divided by h bar corresponding to path. And we made an analysis of this action for a classical path. So the first observation is that the classical path that are connecting these 2 points in time tau, they can be viewed in a limit that we were interested in, which is that the curvature here, so here we have inverted harmonic oscillators which have a curvature which we denoted omega, that in the limit that we are interested in, that omega tau is much larger than 1, we saw that the classical solutions actually have a well-defined structure and time. Yeah, so the solutions, if we draw them here, so this is the coordinate space, we have q, this is time, tau prime, we are interested in propagation from 0 to tau, and if we start with a configuration at -a, we see that this will most of the time stay at one of the maximum here, it's the left side, and then it will make a transition and stay again at the other maximum. And the transition itself, the time scale for the transition is given by this characteristic energy scale of the inverted harmonic oscillator. So this, we saw that solutions actually have a free parameter, which is the moment, which you can call t0, when the transition happens. Okay, so this is a well-defined structure in time, and the coordinate when this is going to happen is something like a free variable that we can shift. Okay, so and we saw that this at one concrete example, but we also argued that well, this is a general feature just given the fact that well, if you ask what is the typical time to propagate from here to here, it's all determined by how quickly the particle can move away from the maximum and arrive here again. So it's all determined by the curvature here, because the velocity like is the highest down here, while it's the smallest down here. Okay, so this was a very generic thing that holds arbitrary independent of the potential. And then what we did is just calculate the classical action for such a configuration, and we saw that this is just determined by the profile of the potential. Okay, so it's just the integral over the square root of the potential, and there's no dynamical information entering here. Okay, and then we stopped by observing, well, if we are now taking seriously this prescription, the same classical prescription, that it should sum over all classical paths connecting this point to this in time tau, well, in the regime that we're interested in, we can actually have multiple of these transitions, okay? So we came to the picture that, well, start out at here, we can have some transition, then we stay again at the maximum, then we go back, go forward, go back, go forward, go back. And this will be the general configuration. So we call this an instanton solution because this has a well-defined structure in time. And this then is the reverse. So these two can emulate, so this would be an anti-instanton solution. So we arrive at the observation that in the imaginary time formalism we can calculate this transition amplitude by summing over all multi-instanton configurations. And we now have to look at this in more detail. Okay, so this is now the remaining task, calculate this transition amplitude by now summing over the class configuration which we identified to be this bouncing back and forth, okay, these instantons. Okay, so then, let's see what I need. So that was the point to stop. Oh, there's one more thing that we just stated and which we should keep in mind, that this should be checked afterwards. What we will always assume, and this is just based on the physical intuition, that we say, well, the instanton, the quick, like jumping from one maximum to the other one in the real time corresponds to tunneling process. So what we're saying is we can study this transition amplitude by in real time. This would be the particle being stuck in one of the minima, and then at some times it quickly tunnels from one minimum to the other, then stays there again like fixed, and then tunnels again. So based on this intuition we will say that there's always a large separation between the tunneling events, so that the instantons, they have like a time scale 1 over omega for propagation, and what we're saying is that then, after we have tunneled, we will, let's call a typical time tau, we will stay at one of the maximum, okay? And this time is larger than this 1 over omega. And this just means that we can sum over multiple, like these instantons, but they are, in a sense, dilute, that they don't interact with each other, okay? So this is an assumption that we will do in the calculation, and that we have to check to verify afterwards self-consistently. But this is one assumption which is just based on like physical intuition of the problem. Okay? So we are thinking about a dilute instanton gas. Okay? Okay, so then what we want to do, so the first part A was the classical analysis of the problem, meaning solving the equations of motion in imaginary time now. And the second part is really calculating the transition amplitude. And so as said, transition amplitude in imaginary time and in semi-classical approximation. And just to have the information once written down again. So this is Q, this is A, this is minus A. This is time tau prime. We're interested in 0 to tau, and we have these multi-instanton solutions, which are classical solutions, connecting minus A to A in the imaginary time tau. And this is now called just an instanton configuration. I mean, it consists of instanton and anti-instantons, and it always has to have one instanton more than an anti-instanton. But let's not just differentiate between anti-instanton and instanton, just call it instanton. because they also have, so this would be instanton configuration. What we've already calculated was the action of such an instanton, which is just given by the integral from minus a to a q. Where was this? And well, this is, as said, the same. So this is the same for the instanton and the anti-instanton, and doesn't depend on any dynamical information, like it doesn't depend on when exactly the transition happens. So given all this, what we now want to do is to express this amplitude as a sum over, let's say, n, an n-instanton configuration which has to consist of an odd number of instantons. No? I mean, as said, so instanton and anti-instanton are both called instanton. So we have to have n being odd contributions to go from minus a to a. And then we can just use that we can shift around for a given n configuration of these instantons, we can shift around these times freely. Okay, so we saw that the classic solution and the action doesn't depend on the time when the instanton happens. So this means in such an n instanton configuration, we have n free integrals which correspond to the time when each of the instantons are going to happen. And then what we should integrate is the amplitude for a given n instanton configuration with the instantons happening at time 1, t1, t2, and so on, tn. Okay? So this is the object that we want to calculate, and in the semi-classical approximation that we're interested in, this object here, this transition amplitude for an n instanton configuration, is just given by the classical part, which is always of the form minus s classical in imaginary time divided by h bar, and then a quantum contribution which is due to the Gaussian quantum fluctuations. So the quadratic approximation integrate over quadratic fluctuations. Okay? Make this consistent. I mean, they both depend on this multiple, in principle, both depend on this multiple index of times. Okay? So let's look at these two contributions separately. First, at the classical contribution. Okay? So the classical contribution, which is just the exponential of the classical action. To calculate this, so what did we calculate here? This was the action for one instanton solution. Okay. So now we observe that when the particle rests at one of the maxima, you do not accumulate any action. Okay, so we just set the potential there to 0, so you could send it different from 0, but then it's just a phase factor which in the end doesn't play any role. So you do not accumulate any action when you're at rest positions. So in the end, an n-instanton configuration will just accumulate the classical action consisting of the sum of these contributions, which is just the sum of all these classical actions. So we get n times this classical action here. Okay. So we just have to sum the contributions from each bounce. And if we have n bounces, well then this contribution here, τ2 and so on, τn, is just given by e to the minus n instanton divided by h bar. Okay? where this is defined here. So we make an important observation that the right-hand side here is completely independent of the times when this is going to happen. Okay? And as said, what we always implicitly assume is that these objects are independent of each other, like we have the dilute gas approximation. Okay? So this is independent of the instance how I in the transition is going to happen. So that was the first part. Now let's look at the quantum contribution, which comes from the quadratic fluctuations around such a given classical solution. So there is, again, the observation, we can divide the problem into two contributions, namely once when the particle sits at one of the maxima, and then the contribution of the transitions. Now in this limit, just say it once more, that we are interested in, these transitions are just a negligible contribution in the overall, because most of the time the particle just sits at one of the maxima fixed. So if it sits at one of the maximum, then we're just considering the inverted harmonic oscillator problem, no? So in real time we're stuck at the minimum, so we are considering for most of the times in this regime we are interested in, we can say the dominant part, all that we have to consider is just the quantum fluctuations corresponding to those of an inverted harmonic oscillator. Okay? So, let's say here, so when the particle rests, that means when the time variable is in between, let's say, two instants of tunneling, so tau I minus 1 and tau I is the tunneling point, or the instant, the changing configuration. So in this interval, the particle rests, and there the quantum fluctuations are those of an inverted. And inverted again because we are considering imaginary time formalism, harmonic oscillator. Because it should be good to approximate the potential by this quadratic form. So this means that we can immediately take. So this now still corresponds to the quantum fluctuations, so to the fluctuation determinant which you get from such a time interval. Okay? So we know that the harmonic oscillator has a fluctuation determinant which is sine of omega, and then the time spent, so here it would be tau I minus 1. And then because we are here considering imaginary time formalism, you may check this again, so this would just correspond, instead of studying the transition amplitude for the harmonic oscillator, like the time evolution propagator, this is also what you get for the density matrix element of an harmonic oscillator. You may verify this. Yeah? This you get the I. So now in the regime that we are interested in, where omega times tau is much larger than 1, so this is a sine hyperbolicus, so we have an exponential large, exponential small term. You only have to keep the exponential small term, so this would be given by omega tau I minus tau minus 1. And then there's a factor 1/2 because it's a square root. Okay? So this would correspond to the fluctuation determinant for such an interval, and now we make the statement, so just use the statement that, well, we have dilute gas, so to get the overall amplitude, we just have to multiply those contributions from here, from here, from here, from here, from here. Because we say that fluctuations around the bounces can be neglected in the dilute approximation. So fluctuations around bounces in first order can be neglected. The first order approximation is in first order. Since what we said is that this is much larger than 1 over omega. So the dilute gas approximation. Just who would be interested to see how you can do the calculation including all this? So you may want to look in the book by Saint-Justin, who discusses problem in more detail. So you can also, if you want, by putting more work into the problem, also consider fluctuations around the bounces. But I mean, this is not of so much interest for us here because we just want to see in principle how this non-perturbative approach here works. And I mean, you can make approximations that we do here better by just putting more work into the problem. Okay, so we have then with this approximation, we find that the quadratic fluctuations, the fluctuation determinant for the n instanton event or configuration is just given by the product of these contributions, tau I minus tau I minus 1, divided by 2. And here I used, like, just to get the right order, I mean, there's here prefactors from the fluctuation determinant, and there's factors 1/2 and whatever. So let me just introduce here a factor k, which would be correspond to exactly all these like prefactors pi and whatever, which is not an unknown, but this is just let's say a pyramid of our laziness. I mean, we could include it, but we just don't want it. Okay? So if we then do the product, well, we see that the product converts into a sum here. So what we just end up with is all the time differences, which then will give us the overall time, no? So if we do the product, we get a k to the n, and then a minus omega tau half. And we again make the important observation here that this is again independent of the instance when the transitions actually happen. So again, just depending on the total time, in this case here now. And we used, as said, this dilute gas approximation also. Use dilute gas approximation arrive at this expression completely independent of the instance. So we have we have found the two contributions. Now we just have to write down the expression that we had for the transition amplitude and insert what we have found for the amplitude of an n instanton configuration in the semi-classical approximation. So in the semi-classical approximation, so let's write this like this: semi-classical and dilute instanton gas. We arrive at a sum over odd integers, where we sum k to the n. And then we can just, the amplitude, I mean, doesn't depend on tau, so we can just pull everything out of the tau integrals that we had before. So we have a minus n as instanton divided by h bar, and a minus omega tau. So why don't we just make it more organized? Pull this out also, e minus omega tau half, and we have the independent terms. bar, and then we still have the tau integrals that we had, no? So we said that, well, we can choose the origins of the times when the instantons happens to just freely. So we have here this n instanton configurations we can integrate over n times when the instanton is going to happen. So this will just give us a factor 1 over n faculty tau to the n. Okay, because, I mean, giving up the order, you get factor n faculty, and then you get the tau to the n. So, this is quite a very interesting expression. I'll try to explain why. So, we saw that the transition amplitude can be given by this sum of all instanton configurations. Now, there's two contributions. There's one contribution which just wants to suppress many instantons to happen. And this is just given by, well, n times the instantons. So the larger the number of instantons, the more this will be suppressed. So this is a term that suppresses instanton configurations, and in a way you can think it's just costly for an instanton to happen. So you have to pay some price in terms of an action for instantons to happen. So say energetically it's the best to stay at one of the minima and not to any transition. But then we see that because we observed that actually we could put the instanton wherever we want to, so we had the zero mode, which is the time when the instanton is going to happen, completely freely. This gives us here a factor which enhances this amplitude. So we have two competing processes. One is like an energetically suppression of instantons. One is just which gives us like the free choice to choose where the instanton is going to happen. This is like an entropy factor. Yeah. So it's like saying we have here a timeline, and now you can put wherever you want the instance where it's going to happen. You can put them wherever you want to. So we have like an entropic factor, yeah, which is just from the phase space volume of the configuration, yeah, because we have like a large phase space volume of configurations, an entropic factor which enhances the amplitude. So we have two competing processes here, okay, and this is like a very generic thing that I'll try to make a link of this transition amplitude afterwards to one problem of statistical mechanics where you're interested in phase transitions. And there, this is like the thing that always happens. You have a competition between something which might be energetically costly, but since such a process that might be energetically costly may give you some large phase space value, when it's going to happen, you have an entropic factor which competes with it. Okay? And this can drive phase transition or destroy them or whatever. Okay? So this is one observation we come back to. But technically now, this is nice because we have 1 over n. Facultative, we have a number which is tau times k times e to the minus s int to the power of n. So we have just a potential series of all odd numbers, which is just the sine hyperbolicus of the k and then e as instanton h bar times tau. Okay, so we can now just sum this. So keeping the first factor e to the minus omega tau half, and then writing this here, you get a sine hyperbolicus k tau e to the minus s instanton of 1 instanton divided by h bar. So this is the answer to the problem that we asked, what is the transition amplitude we were interested in. Now, the original problem we were interested in is actually where tau is not tau, but it. But now we can use exactly what we said. So we look at this function, and we see that, well, this is completely fine to analytically continue from tau to it. Okay, there's nothing dangerously happening because these are completely analytic functions. So there's no problem to do the remaining step, which is the analytic continuation. simple, it can be more complicated, but here it's very simple. Which then corresponds to the object that we were interested in. So you get from the sine hyperbolicus, you get an I sine, and this gives you an e to the I omega tau half. So minus I sine a tau e to the minus h bar. Okay? So this is what we get for the transition amplitude, and then squaring this gives us a probability. Now we can compare this to the initial result that we got from the simplified two-level model, no? Well, we just said, well, to get some idea of the problem, let's just map this problem to saying we have two levels here, which correspond to some energies epsilon 0, and then we have some finite amplitude for tunneling. So let's call this delta epsilon. So just describe this tunneling problem by a 2x2 matrix, where this stores information about the transition, and this is just the energy. Now what we got from this calculation was exactly this form here, no? So we got that you have just a dynamic phase factor where the omega half corresponds to epsilon 0. Yeah? So the general problem, we had introduced this epsilon 0, which now here is given by omega half. And the delta epsilon was just, here now just corresponds to k tau e to the minus, that's instanton divided by h bar. Sorry, not the k tau, just we had delta me times t, no? So delta e corresponds to this. So that's quite nice, because we see that the simple model actually has, all the right physics, but what we now see is that we can relate these like parameters that we introduced, the phenomenological parameters, to the microscopic details of the problem. So this is the curvature, this was related to the second derivative of the potential at 0. And you see, well, you just have the energy, this is just the ground state energy of the harmonic oscillator. So you just have a dynamical phase factor due to the harmonic oscillator ground state, say oscillation. You see that this is coming from this one here. And then you have that here would call, like if you don't have these, you have the eigenstates which are 1, 0 and 0, 1. And if you introduce this, you mix the two states, it's called the hybridization or whatever. This is given by, well, the parameter here is not so important because we are only interested up to like the exponential part here, so it's exponential depends on the instanton action. Okay? So this is tells us then that, well, the tunneling events or the tunneling probability is determined by the or the time scale on which the tunneling occurs is determined by the instanton action. Okay? So that was the instanton calculation, and as said, like one can improve this, and who wants to see more details can look into the large quite soon just now. Okay, so any questions here? So there's still one thing we should do, and this is what we used here, is that we said that we use a dilute instanton gas approximation. This we should still verify. Okay, so let's see if we can see that what we found now self-consistently confirms the rightness of the approximation of saying that the instanton gas is dilute. So let's just introduce some notation. So let's call this average n the typical or average number of instantons that contribute to this transition amplitude. So they contribute to the transition amplitude for a given time tau. So if we introduce this, then what we should verify is, well, that the distance between the instantons is large, and this means just what, so we have to compare two scales, that is the transition for the instanton, I mean the structure itself has a structure as 1 over omega, and this should be compared to the typical time that the particle rests in between such tunneling. So the typical time between tunneling is just the overall time tau divided by n, and this should be then larger than 1 over omega, okay? So we should verify that this would correspond to like one of the plateaus, no? And these plateaus should be larger than this here, so this should be larger than 1 over omega. Okay, so we have to verify that this is given. So what we need to have is the typical number of instantons that contribute to this expression here. So we saw that this transition amplitude, we can write it as the sum over all n, over all numbers. And what we summed were, in a way, you can think of, you sum contribution from one instanton, 2, 3, and whatever, and what we sum is just the weight of an individual instanton, okay? So what was in this, so this n-dependent factor, so we had the sum over n, and then we had some, let's call it Wn. This was just given by the e to the minus n times instanton action, tau to the n divided by n faculty. So this gives the weight of an n instanton contribution. Okay, so let's introduce the weight of an n instanton configuration, so the weight in the transition amplitude. Let's call it Wn, by tau to the n, k, e to the minus n, that's instanton divided by h bar, and then okay, so now if we want to calculate the typical number n, what we have to do is we just have to make, let's say, the average, that we say the sum over all possible configurations. A configuration with n instantons has a weight n, and well contributes to this average just by n. Now, just to normalize this, we have to normalize our weight, so we divide by 1 over n. Okay? And here, in principle, we should sum only over the odd contributions. Okay, so this will give us the estimate of the typical number of instanton, just noting that this gives us the statistical weight of an n instanton configuration. Okay, and this is just an observation. Now, to calculate this, we can now already anticipate or then verify later on that the n should be a large number. That's what we expect if omega times tau is larger than 1. So if it's a large number, let's don't care so much about factors of 2 or whatever. So let's forget about n being odd. This might be, we're just interested in orders of magnitude. So if we forget about n being odd, we see that, again, so this is just, let's say, of the form x to the n divided by n faculties, that's the exponential series. Now here we have a factor of n. So if we shift in the above sum, if we put out, so we have n faculty times n, which gives us a 1 over n minus 1 faculty. So if we put out an x, we reproduce the exponential that cancels against this. So this will just give us a factor x. Yeah, so I'm just saying that if we have x to the n divided by n faculty times n divided by x to the n faculty, that's the expression that we're interested in. You can write this as x times x to the n faculty, x to the n faculty, just using here that this is 1 over n minus 1 faculty, and if we put out a factor of x, okay? So this just gives us x, okay? So if we use this, and we recall what is x, and this gives us this tau, to e as instanton h bar, and again, there's a factor of k, but this we shouldn't be. No, there's also factor k to the n, so we can put it in here. So this is what we find. We should put of the order. We're just interested in the parametric dependence. Okay. So this then tells us that well, n over tau is just given by k to the minus s instanton divided h bar. And what we wanted to verify is that this here is much smaller, much larger than omega. So let's write this. So we need some estimate for the instanton action, and what we said is that this is given by the integral for minus a to a, this 2m square root of e. So if we just want to get an estimate of this, we can again just look at the contribution from the, let's say, from the close to the maximum, close to the bottoms. Okay, so this is from the harmonic oscillator part. So what we would have here is m times omega times q minus a integrated over a. So this will give us something like m omega a squared. Okay, of the order. So we find that this is of the order of e to the m omega squared a divided by k divided by h bar, and the condition that we need to be in the dilute regime is that this is larger than omega. Okay? So this is a restriction that we have, but we see that this here is exponentially depending on omega, so it should be always fine to go to this region. Okay, so this is what we need to satisfy for the validity of dilute approximation, and we see that, well, this is not the real problem for us. Okay. Okay. So questions or? So this was the calculation for this transition probability, which one can also calculate with WKB and so on, but I think it's in a very controlled way, so one can improve all the approximations. Now, what is really the nice thing is that, okay, so the first thing I think is nice that here you see that the power of the path integral, like how flexible it is. No, that's what I said in the beginning, like if you allow for imaginary times and all this, it's very flexible, so you can do these kind of tricks of transition to imaginary time to calculate this. But what is more maybe importantly than just being like this, you have these nice technical tricks to do the calculation, is actually the connection to other fields. So this is what I'm going to talk very briefly, like still is that, well, this is related also to a problem from statistical mechanics. And this is again related to the thing that we said before, like the path integral is what? Is a sum over paths. Like you have a quantum problem of a zero-dimensional object of a point-like particle, and it's related to some integral over paths which are all weighted by some weight which in imaginary time is just, I mean, like Boltzmann wave. So this is related, the zero-dimensional quantum mechanics problem is related to the classical statistics problem or 1D problem. So we can use this intuition now to relate this to a problem in magnetism. And this is what I just briefly still discussed, maybe make 5 minutes break.